So finally, the final thing here is that now that you've learned these energy formulas, this formula here, power is work divided by time, we can actually generalize here. That work can be any change in energy. Any change. Right, so it could be an MGH, right, like as in we lift something up. It could be that we speed something up, so it could be kinetic energy, right? Okay, it could also be a change in kinetic energy, right? Change in kinetic energy would be we go the final kinetic energy minus the initial, right? VI squared, right? Okay, so it could be any of these guys could be our change, or even, you know, we could write problems. I'm not going to really go there, but we could go up a hill and speed up, right? That could be our change in energy. Okay, so let's look at the first one here, right? You're an engineer. You're designing a pump. It's got to pump out 3,400 kilograms or 3,400 liters of water, 4.5 meters out of a basement, right? And the minimum power rating, of course, the motor is not 100% efficient, so it'd have to be more powerful than that, right? How would we figure that out? Well, I think that the work in this case is going to be the MGH, right? We're lifting a mass, some height, right? And so power is work divided by time. And instead of work, I'm going to use potential energy, right? MGH divided by T. And I know we could have done this, by the way, using our jambalaya technique, right? But this is a shortcut, just one step, right? So 3,400 kilograms, right, times 9.8 newtons per kilogram. That's my son drumming on the floor upstairs, right? And then the height is 4.5 meters. All right, so 3,400 times 9.8 times 4.5. All right. What is that? 149,000. Okay. Oh, we forgot to divide by t. Okay, so divided by 1 minute, right? That's 60 seconds, right? Okay, so I've got that, and I'm going to divide by 60, and I get that the power is 2499 watts. And we only have a couple digits here and a couple digits there, so really we have to say it's about 25 watts. Or you could say 2.5 kilowatts. Yeah? Or you could convert it to horsepower, or, you know, whatever you want. All right? I'm going to go to the next, one more example of this, and then we've got, okay, so a sports car speeds up, so this is the mass, right? From rest, so our initial velocity is 0 to 27.2. That's 0 to 60, by the way, in 3.5 seconds. What is the average power output? Well, I think the work in this case is 1/2 mv squared, right? He's drumming away up there. Okay, 1/2 mv squared. So the power is 1/2 is going to be the power is work divided by time, right? And I think that's going to be 1/2 mv squared divided by t, right? And of course this is average. I think at first it's not as big a power output. At the end it's a lot. But on the average it's this, so I'm going to go, it's 1/2 1280 times 27.2 squared divided by 3.5. Okay, so I'm just going to do that one swell foop here. 0.5 times 1280 times 27.2 squared divided by 3.5. Boy, I get a big number. It's 135,285.0. I'm going to say just cut it off right there. Okay, that is 135 kilowatts, right? 135,000 roughly. Okay. So that's in general what you're looking for, right? You just, for work now, you can substitute any change in energy, okay?